Okay, so this is the last question we need to solve for this exam. And I am sorry for the coughing noises in the other video, that I am in a position that I cannot help it right now since I'm a little bit sick. So in this question we have a well of 1 femtometer length. So this well, you do not have to really think of it as a physical well that allows you to move in lots of directions, but what it does is that it is such an object that restricts you to move in one direction for a given amount. So this is the length of our well, and we just put a proton in the well, and we have to find the approximate kinetic energy of the proton localized within such region. So again, as we used in the previous question, we used the uncertainty principle. Now I have to make a little bit of an explanation here, that why do we use this. Now that we have put this relation, we know for certain that this is going to be smaller than 1 femtometer, but since we do not specifically know what is the accuracy of our measurement method, we might just take that the uncertainty in the position is the length of the well, since this does not hurt this overall inequality. For example, I could have actually measured any random point at this well to be the position of my proton, but the proton may have had to be at the other side. So actually it might be that my measurement method is as accurate as this well's length, because I only know that my proton is in the well and not outside, but I actually cannot measure anything more than that once I put it in there. So also, like, taking this larger does not hurt this equality at all, but like, even if I took it smaller, if I had took this uncertainty in the position to be small, my uncertainty in the momentum would have to go larger, since this is a constant, and it would have hurt my inequality a little bit, that this has to go larger. So let's just put all of this together, that we know that 1 femtometer, this one, is like these are all constants, and I quite frankly do not like doing anything with no constants, putting in their actual SI values and stuff like that. So but I think in this case we can't really help it, because your answer key calls for some numerical answers here that I actually did not do in my first video, but after I received the key I just had to revise this question again, so that we might have just have something numerical at our hands. Now that at the first page of your exam papers you were given some constants and their numerical values, etc., and the H was not in there, but HC was there. So we are going to just multiply C, divide by C, and then we are going to obtain something like this, that P is bigger or equal to HC over C and 50. Okay. Meters. Okay, so if we plug in the values over here, HC we know to be this number, Now, this is, it says that we may take pi as 3, and the rest mass of the, we are going to use this in a second. Then 12, 15 meters cross 8 cross over 3, 8 meters again. Now, if we work this out, if I have to work this out, what would it be? Maybe I let this stay as C for now, so that I can have a quantity as electron volt C. So this is gross 9 meters over 12 minus 15 meters. Okay, and that is mega, and this is let me check my calculator. I am not really good at doing this at all. 12. Okay, this is 103.3 mega electron volts per C. And now that we have our momentum uncertainty in the momentum larger than this. Now, peeking into the answer key, I see some assumption is this. Like, one might ask why? Because because our valve is so tiny and small that we just could have took and it's only one dimensional, and I know for certain that my photon is in this well. I just took a chance and said that my uncertainty in the position is going to be as large as the valve's length. But then since that was so small that this like mega electron volt level of discrepancy in the uncertainty in the photon's momentum is quite large. So I might just assume that it has the same order of magnitude as its original momentum, so that it does not have so much momentum that I can have such an uncertainty in it. It because I basically did not actually measure anything for the position. Now that I am not actually measuring it for the momentum, I am just putting it into the well, and I know for certain whatever the photon does, I know for certain that unless it is in the well, and I can just randomly pick a position, and my uncertainty would be still so small. I could have just picked any random position in the well to be my proton's original position, and at this number, 1 femtometer would be the largest it could divert from the random position that I picked. So it must be just that it can only divert from its original momentum as this, which is already big enough, but small compared to the rest energy. So because think about it, this is like 100 mega electron volts, and the rest energy we just take it as 1000 mega electron volts. This is 10 times. This is 10 times larger than, 10 times smaller than it is rest energy. So it's kind of like small compared to its rest energy, that I just take it to be the momentum. So we just write our trusty equations for the kinetic energy like this, And now find numeric values as this. It's 103 mega electron volt. See, I square this thing, and this is 2m. Then I know for certain this mega electron volt square 2mc square, but that mc square was 2mc square, or rest mass, was given approximately 1000 mega electron volt. And then I can just divide this. Now that is going to give me I think that's going to give me about like 1 mega electron volts. I'm just double checking with your answer key that I'm just seeing something like 5, which I don't quite get. And oh, okay, so like this is 200 mega electron volts, and then this is 1000. I think there's a little bit of a mistake in here, that I have to have something like 100 squared. Okay. Okay, 10,000 mega electron volts squared, 2000 mega electron volt. This mega electron volts just goes to hell together, and yeah, this is 5 mega electron volts. Okay, this is 5 mega electron volts is the kinetic energy of the photon localized within this region. Now in part B we have to find the corresponding energy of an electron. So like it only makes sense that we found its kinetic energy, we found its momentum, that we have to find its total energy. Then we had written in the last recitation that relativistic total energy formula was this. Remember? Now, as we had written this, now we know we had found PC to be. What did we find PC to be? 100 mega electron volts. Yeah. 100 mega electron volts square. This one. Then mc square we know to be 100,000. I am so sorry. Oh, I'm sorry. Now this is the. It was for the proton that we had done this, but now it is for the electron we have to do it. And for the electron, how do we know? How do we know this for the electron? Okay. Okay, we only have to need the rest mass of the electron, which because now it does not matter. It does not matter that this was the proton or the electron or anything else that we found its momentum for it because we just quite frankly did not use anything but some constants and the length of the region. So anything in that region would have had that sort of momentum, but the rest mass is going to change a little bit. So, and this for the for an electron is going to be 1 over mega electron volt square, because mega electron volt, like the half of the mega electron volt is the kinetic energy of the electron. Then, since this is too large, this is too small, we're just going to ignore it and just going to say that this is 10,000 mega electron volt square. So, and if we are going to find the kinetic energy of it, we are just going to just remove it from its rest energy that we have found to be 100 mega electron volts. Because this was squared, we took the square root of this, and we now have this half mega electron volt again is the rest energy of the electron. That's 99.5 mega electron volt will be the kinetic energy of some photon electron in this well. Alright, and that completes the video.